Welcome to lecture 23 of partial differential equations. Today we'll be looking at ways of solving the wave equation on an ellipse using separation of variables in the first part of the lecture, and during the second part we'll be taking a more careful look at the so-called Sturm-Liouville problem. That's a problem in ODEs rather than PDEs, but it has direct application when we use separation of variables to solve PDEs. Okay, so last lecture we looked at a number of separable coordinate systems, and I want to use it in this lecture as an example of how you go about solving the wave equation on an elliptical membrane using separation of variables. So we have the wave equation with the Laplace operator and the second time derivative, and the Laplace operator is just the second derivative with respect to the first Cartesian coordinate and plus the second derivative with respect to the second Cartesian coordinate. We're working in 2 dimensions. And the first step is to separate the time and the spatial variables. And the way we did that is we made the ansatz that psi is the product of a function of time only and a second function phi of position in x1 and x2 only. And what we do is we substitute this ansatz into equation 1 and then divide by psi, which is basically f phi. And what happens then is we get the Laplace of phi, which is now just a function of the spatial variables, divided by phi from the first term. And we move this to the right-hand side, and we get 1 over c squared, the second derivative of f with respect to t over f of t. And as said in the last lecture also, because the left-hand side is a function only of spatial variables, the right-hand side is a function of the time variable, and this has to hold for all space and time. This thing can only be true if each equation is independently equal to a constant. We're going to call that, for the purposes of this particular equation, minus k squared, which is the separation constant. And using k squared, we can now write down the equation for the time evolution of f, and it's just f second derivative is equals to minus omega squared f, where omega is just another constant that's dependent on c and k. So we have omega squared is equal to c squared k squared. And we can go about solving this thing directly. It is actually the simplest example of a Sturm-Liouville problem that we'll look at in the second half of this lecture. But the easiest way to solve it is it's a second order equation, you have 2 independent solutions, and you make this ansatz e to the alpha t, and you solve alpha, and what you then get is you can find that alpha is basically I omega, and you can rewrite it as a cos omega t b k cos sine t. Okay, and please note that these constants are constants. I've put the sub-index k because implicitly omega depends on k, and while we haven't yet proved it in this part of the derivation so far, eventually we're only going to have discrete values for k that are allowed. Okay, and that's going to come from the boundary conditions in this when we look at the problem more closely. But basically I'm going to label for every different frequency, you're going to basically have a different time evolution for some of the spatial partial modes. So I'm going to label k, f of k, f as a function or sort of as a subscript k, just to indicate that f implicitly depends on k, and omega in fact also just depends on k. Okay, so now that separates out the time part. We now want to solve the spatial part, and particularly we want to solve the Helmholtz equation. Laplace phi is equals to minus k squared phi. And the domain we chose, or just for illustration purposes, is an elliptic domain. So let me just introduce you quickly to an ellipse. It sort of has 2 radii, a larger one, a smaller one. On the axes of the larger radius, you have 2 points that they call the foci, and this I've indicated by minus d and d. And why, for example, would anybody want to solve the wave equation on the ellipse? And the answer is there's many reasons, right? Firstly, solving the wave equation on an ellipse and a circular membrane results in different frequencies, just as solving the wave equation on a rectangle, which you must probably do in a problem set, also results in a number of different frequencies that can be observed. So they have different acoustic properties if you're looking at an instrument. Also, if you have a house, right, if you for some reason want to build an elliptical house, then you get past your builder who says, there's no way I'm going to be able to construct that crooked wall, which actually is an easy thing to do, because if you tell him you want to construct an ellipse, all you have to do is hit in 2 strong steel pegs at the foci, and you have to attach a steel cable of a fixed length that's very strong. And then to trace out the ellipse, all you have to do is you simply take the cable and put a point in the cable, and you move it. And the cable actually will trace out the ellipse. So it's an easy way of drawing an ellipse, in fact. So you can get past how you make the shape. But if you want to look at the acoustics properties of a room like that, you would also want to solve the wave equation on an ellipse. Okay. Another example is why you would want to solve the wave equation on an elliptic membrane. Your tympanum, in the way you hear, is potentially an ellipse, and the vibrations and frequencies to which your eardrum is sensitive is also dependent on the shape. So if you want to understand that, you have to solve the wave equation on the ellipse. So having said that, beyond the practical application, let us return to the mathematical rigor. Okay, so now we want to solve Helmholtz equations, which will basically give us the spatial dependence. And the solution domain is basically the ellipse that's expressed this way, where just notice when x2 is equals to 0 on the x-axis, the boundary is x1 is equals to r1, as expected. When x1 is equals to 0, the boundary is r2. Okay, the foci you can get in terms of r1 and r2. They're at plus minus d, but d is just equals to the square root of r1 squared minus r2 squared. And your eccentricity is equals to d over r1. So the eccentricity is an indication of how spherical or non-spherical or sort of how flattened the ellipse is. So if d is equals to 0, right, r1 is equals to r2, and e is equals to 0, the maximum value for e for an ellipse is 1. Okay, then the ellipse is almost becoming sort of a flattened straight line pancake. And in terms of R1 and R2, there we can express the eccentricity as well. Okay, so now in order to find an analytic solution to Helmholtz equation, you have 2 things. You want to seek a set of coordinates that are specified to the boundary on which your boundary data is specified, as well as the domain on which your initial conditions are specified. And for this purposes of this example, we've chosen this particular ellipse. And there's a second condition, right? You want the Helmholtz equation to be separable in those coordinates to find an analytic solution. Okay, so if you notice that the Helmholtz equation is actually separable in Cartesian coordinates over here, because you have the separable operator and k squared is just a constant, so that's also intrinsically separable. But it is not enough to actually solve the equation on the ellipse. So even though you can separate the Helmholtz equation in the Cartesian coordinates, you can't actually specify the boundary conditions successfully. You actually have to have coordinates to get an analytic solution where you have a single coordinate that is constant along the boundary. And this we can actually do for the elliptical case. In fact, as I pointed out in the last lecture, there are very few coordinate systems in 2 dimensions in which this is possible. And we made a complete list in the last lecture. And now we're just going to explore the elliptical coordinates. Okay, so in the previous lecture, we showed you how you construct the transformation to the separable coordinates on the ellipse. And just to summarize them, you first make a complex number that's made out of where the real and the imaginary part are your 2 Cartesian coordinates. You make another complex number which is made out of the coordinates you want to transform to, in which the equation becomes separable and for which one of the coordinates are constant along the boundary. And for the ellipse, the transformation is basically characterized by z is equals to d cosh of w. And that results in the real transformation, if you look at the real imagined part, of the x-coordinate equals to d cosh psi1 plus cos psi2, and x2 is equals to d sinh c1 plus sine of c2. And just to give you a feel for what these coordinates do, the first thing is to observe at constant, let's call it C1, right, you are going to characterize this whole boundary. So in particular, when x1 is equals to r1, then cosh of c1 star is the coordinate that characterizes the outside of the boundary. Okay, so all I've done is put r1 there and divided by d. Psi 2 is viewed as also being equal. If x1 is equals to r1, then psi 2 must be 1. Okay, so you're at that point. Therefore, r1 is equals to r1 over d is equals to cosh 1 psi 1. And at the same time, if psi 2 is 0, this is 0. So you're on the y-axis. Similarly, if you go, and you can also see from the definition of your eccentricity, we can immediately get the eccentricity in terms of this outer coordinate. Sig1 is just 1 over the cosh of it is just 1 over eccentricity. The second case, if you look at C2 is equals to pi over 2, you can also see that then the x coordinate is 0 and the x2 coordinate is maximum, so the y-axis. And you have that R2 over d is equals to sinh c1. Okay, so there's a direct map between the constants describing the ellipse in the Cartesian coordinates and the variable c1 you choose, or the outer variable c1 you choose. In some sense, you're defining the range of c1. Just other thing, it goes from the maximum value of c1 star that's on the ellipse to a minimum value of 0. So look what happens if c1 is equals to 0, you have x2 is equals to 0, and this is equals to 1. So you basically have x1 varying from d to minus d as c2 varies. So the line or the ellipse, if you would call it, that's described by c1 is equals to 0 is actually this degenerate ellipse that lies between minus d and d. So as c changes, you go from the outer boundary in to minus d and d. Okay, just to make the discussion complete, for this particular picture that I drew, I chose r1 to be 8, r2 to be 4. That immediately gave me that d is equals to r1 squared minus r2 squared, which is 4 square root 3. E is just equals to d over r1, so it's square root 3 over 2. And then C1 you can calculate by taking the arc cosh of R1 over D. And we just get about 0.55. And so with our coordinates, we're going to consider the coordinate regime to describe the interior of the ellipse is simply C1 from 0 to C1 star. And C2 is an angular coordinate that you can immediately see from the way it's used here to describe x1 and x2. It simply goes from 0 over here all the way around to 2 pi. Okay, so what we're going to do now is actually do the separation. Okay, so we've transformed to the new coordinates, but we need more than the coordinate transform. So here's our coordinate transform. When we transform the equations, we needed that factor of g1 prime, which actually came from the derivative of the coordinate transformation, which, since it's expressed as a complex function, is very easy. It's just dz dw, so it's d sinh of w. Okay, and having given that, we could then write down the Helmholtz equation in the new c1, c2 coordinates, which was just the Laplace operator in c1, c2, with this factor that's dependent on the coordinate transform multiplying out k squared phi. And so let's just compute this factor for our particular transform. We already have g prime, so we just want to choose compute the norm squared. Okay, so that's simply d sinh w multiplied with its complex conjugate, so it's d squared sinh w since w bar, and just sinh of w, where w is c1 plus I c2, can be written out in terms of real functions as sinh of c1 cosh of c2 plus I cosh of C1 sinh of C2. It's just complex theory. And you want to find the norm squared of that, so you have to multiply this thing with this complex conjugate, which basically means that it's the sum of these two things squared. Okay, and there we have it. But now there's a catch, right? In our derivation, we said that in order for this equation 1 to be separable, this factor actually has to be separable. And at the end of the last lecture, I also mentioned that in fact it is. So we have to do something to this sort of norm squared of the transformation's derivative in order to make the fact that it is separable obvious. Okay, fortunately it is, and the way we see that is simply to replace sinh squared with cosh squared minus 1. Okay, so then that's times cos squared of C2. But fortunately, in order to take this factor out, we have another cosh squared of C1 sin squared of C2. Okay, sin squared plus cos squared is 1, so we're left with cosh squared of C1 minus cos squared of C2. Okay, and if you remember the definition from the last lecture, this thing is separable if you can write this functional part as the sum of two functions of the independent variables separately. Okay, and just for purposes of making this discussion more complete and writing it, and eventually that our equations end up in a form that many people know, you could just use the double angle formula that cosh squared of C1 is equals to a half cosh of 2xc plus 1 plus a half, and cos of C2 squared is equals to cos or half cos 2xc plus a half. Okay, so that's the simplification that I've made there. And now to finally reduce the second order equation in two variables to two independent ODEs, we're going to make the separation ansatz, that phi is equals to the product of two functions of the independent variable separately. We substitute this into equation 1 with g prime given by this thing, okay, and we divide by P1 and P2, and we see that the thing decouples. And this is the way it decouples. When dividing, we lose the phi term on that side, and we're just left with k squared d squared over 2 times cosh of 2xc1 minus cos of 2xc2. The second derivative with respect to c1 is applied to P1 only, and when you divide by P2, you're just left with this P1 second derivative over P1 and the corresponding term for C2. And what we do now is group everything of, say, the C1 variable on the left-hand side, everything that depends on the C2 variable on the right-hand side, and because these two variables are independent, it can only work if each side is independently equals to a constant, and that constant we're going to call B, which is our separation constant. So then we've reduced our second order equation basically into this linear second order ODE for P1 and this linear ODE for P2. Okay, and these are quite famous equations, and they've haunted me for a while, and actually before I started solving this problem didn't expect them to find here. So this is Matei's equation, and we'll have a look a bit more at it so I think next lecture. And this is a related equation. Okay, so just look, these two type of potentials are very different. This one oscillates when you go, C2 goes from 0 to 2 pi, and this one is basically a deep well that it forms with cosh. But nonetheless, we learn how to analyze equations of this type. They are all Sturm-Liouville, eventually they'll all become Sturm-Liouville problems, but we'll look at that more carefully during the second part of the lecture. So what I want to do now is I sort of want to group everything I've said before I actually go onto the Sturm-Liouville problem. In what I've basically done is we've written the solution to psi as the product of three functions of the various variables involved, basically time, C1, C2. C1 is constant along the boundary on which we specify the boundary conditions, and it also defines a domain of integration, spatial domain, C2 is sort of an angular coordinate. Okay, these functions, f depends on the constant k. P1 and P2 have k entering them, as well as an additional separation constant b. And I've put a sum over k and b because we'll show that when we solve these two equations, a and b, these values actually take on discrete values. They are not continuous and they can't be any value, but they are discrete values that come out of here. And that actually helps set the frequencies that the membrane oscillates with. Okay, so we've actually solved the first equation for f, and it's just sine and cosine with this ak and bk, which are constants dependent on k. So for each k and beta, you're basically going to have an oscillating term like this that has a certain spatial description given by these two equations here. But this will become clearer once we actually start finding variables P1 and P2. Just to also recap on what the domain of integration actually looks like and how we'll be using the coordinates to describe the domain as well as specifying the boundary conditions. When we look here, we have C1 equals to C1 star, which defines as blue outer ellipse. As you then change the variables C1 equals to a constant systematically as you decrease it to 0, describes more and more eccentric ellipses until you have something that actually just goes around this line where you have C1 equals to 0. Okay, for a fixed C1, you have your angular variable C2 that starts over here at 0. In fact, this line is the C2 is equals to 0, while the cyan part is C1 equals to 0. So you have C2 equals to 0 over there. And then C increases, and you have a series of hyperbola. Here we have C equals to pi over 6, this line all the way to the axes. And then you have the second one of C2 equals to, 2 pi minus 1 over 6. So that's basically 11 pi over 6 at this part. Here you have C2 at the top part is given by C2 is equals to pi over 3. Down here you would have C2 is equals to 5 pi over 3. Here you have C2 is equals to pi over 2 and 3 pi over 2. So you can see as you traverse a fixed C1, your C2 along the ellipse increases like this. Okay, and so you have the condition on any function of a C2, it's actually got to identify the value of C2 is equals to 0 and C2 is equals to 2 pi. Okay, so that just takes another look at the coordinates. Let us now see, previously whenever we had our partial differential equation that is second order in time, we always specified both size derivative of as at the time t0 as initial conditions. In this case is no different. And these we actually use to fix AK and BK. So to see how this could happen, although I'm not going to make it explicit yet at this stage, at the time t0, size a function only of your spatial coordinates, which we can then recast in terms of our new coordinates C1 and C2. F of k of t, you only have 1 over there. This term vanishes because sine of 0 is 0. So you simply have it, you expand, then you must find a way of expanding your spatial description initially in terms of these basis functions, which I'll get to later, and you can use that then to solve for AK. So then you fixed AK from your initial condition. The same thing, because you have to specify the time derivative of psi at times t equals to 0. The time derivative is just the time derivative of f, which is omega bk cos omega t equals 0. That becomes 1. There's a sine term here that cancels, so you're just left with omega bk times your spatial functions, and therefore the moment you can expand the initial data or time derivative of your wave equation that you're given in terms of these basis functions, you can fix a bk. Okay, so that's just a prescription for fixing the constants actually involved. In practice, I'll tell you how to do that in a subsequent lecture. Now the interesting part, and this is where I said that actually the domain fixes the frequencies of the waves on that domain to a limited extent. So I haven't yet told you how we're going to get P1 and P2, except that they solve these ODE equations, which are second order. They have some potential function of your independent coordinate C1 and C2 respectively. And we're going to choose P1 and P2 so that they satisfy the boundary conditions as well as continuity conditions. So the boundary conditions are simply straightforward. It is on C1, you're going to specify a certain condition of what the membrane is going to be doing. So it can be either, the most common ones are either it's going to be fixed to 0, like you have on a drum or you have on your eardrum, where the membrane is actually fixed to a fixed point, or you can make it that it's free, in other words, that the gradient, for example, at the boundary is 0. But the most common is simply Dirichlet boundary conditions, where you fix the value of the membrane, and the most common thing is to 0 on the boundary. Okay, so you want your boundary conditions to obey these basic functions that you expand your solution into, obey that, much as when we found the Green's function for the heat equation on a finite domain, we also expanded the solution in terms of basis functions that already impose the boundary conditions. We'll be trying to do the same thing here. But in addition to the boundary conditions, okay, we have a thing called continuity equations because of a coordinate change we've chosen, and that's somewhat new. It's an example of a continuity equation. We have, for a fixed psi1, C2 is a coordinate that behaves like an angle. And so a natural continuity equation is that here that you want to find basis functions where the value of P2 at C2 equals to 0 is the same as the value of P2 at C2 equals to 2 pi, and the first derivative is also continuous. Okay, so that would be a boundary condition, an effective boundary condition for C2 or P2. In addition, another continuity equation would be here for your function P1. You've specified one boundary condition here at C1 equals to C star, which is just the one fixed by your problem. You're going to have to specify a second boundary condition along this line over here. Okay, at the other end of the domain, C1 equals to 0. And that one is a little bit trickier. That condition basically has to ensure that as your solution moves across this interface on the x-axis, it remains continuous. And we'll look at that. I actually personally right now don't know how to do that, but we'll find a way. It is done in several other circumstances. And actually, this is why the problem is a little bit interesting for me to do at this stage as well. Okay, and the last thing I wanted to say is in solving for P1 and P2, it's going to determine discrete values for B and K. And while this may not be obvious unless you've had some background in Sturm-Liouville theory, I'm going to make this obvious in the second part of this lecture, or at least start introducing the concepts that actually make it obvious that the second order equation, in addition to having the two boundary conditions at C1 equals to C1 star and C1 equals to 0, is what actually fixes these values for B and K. Okay, thank you very much. That concludes the first part of the lecture. I'll be looking at the Sturm-Liouville problem during the second part.